Welcome to session 4 of transition metals. We're going to be looking in quite a short session today at how we write the electron configuration for both transition metal atoms and their ions. There's some confusion over this, and the way it's sometimes taught, whilst helpful, is technically incorrect and often also makes writing the electron configuration of ions incorrect. So I'm going to teach it to you the correct way, but we're just going to have to accept that parts of this are beyond what we can get over in a video. So this is the way we think about the electrons up to the 4s subshell. Obviously this is the 1s orbital. That's a single orbital that makes up the s subshell, and this is number 1 is the principal quantum number, which says that there is that's effectively the first main shell. Then we've got the second shell here broken into an s subshell and a p subshell with 3 orbitals now in the p subshell. Then over here, all of this makes up the third full shell, or the third principal quantum number, with a s subshell, a p subshell made of 3 orbitals, and a d subshell made of 1, 2, 3, 4, 5 orbitals, and the 4s subshell. Sometimes you'll see the 4s subshell moved to be in between the 3p and the 3d, and sometimes you'll see it drawn as a lower energy. Sometimes both of those. That is in fact incorrect. The 4s subshell is definitely a higher energy than the 3d, but there are some circumstances in which the 4s subshell fills up before the 3d does. And I'm actually going to show that to you now with an example. And the example I'm going to have a look at is vanadium. It might be helpful for you to have a periodic table with this, so if you want to pause the video maybe to go and get one. But you will find out that vanadium has 23 electrons. So let's start putting them into our electron orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that I started filling them up unpaired first and then paired, so we're up to 10, 11, 12, 13, 14, 15, 16, 17, 18. Now we have a problem because we've got 5 more electrons to get in here, and we know that something unusual happens around here. So I'm going to first of all put 2 electrons in the 4s, and we're just going to say that it fills up first for now. Technically that's not exactly what's happening, but we are just going to accept that the 4s fills before the 3d in most cases, but it is still definitely a higher energy than the 3d. So that leaves us 3 electrons which are going to go in unpaired in the 3d subshell. When it comes to the shorthand convention, so rather than us having to write all of this out every time, we know that hopefully when we put AR in brackets, that means 18 electrons, and it's equivalent to 1s2, 2s2, 2p6, 3s2 and 3p6. So all of that we can account for. We're only particularly interested in the 3d and the 4s. So if I was going to do this for vanadium, I'd recognise there's 18 electrons in there. I don't need to write 18 under there, that's just to help me remember. 18, 19, 20, 21, 22 and 23. So let's have a look at some examples, and this is where your periodic table might help when I will tell you how many electrons they have. So I'm going to have a look at scandium first of all. Scandium has 21 electrons. I'm going to subtract 18 of those electrons because those are the electrons that make up the argon core, which means I've got to put 3 electrons into the 3d and the 4s subshells. So I know that 2 electrons go into the 4s because the 4s fills up first, and the remaining electron goes in there. And if I want to write this out in even greater shorthand, I would go AR in squared brackets 3d1 4s2. Again, sometimes people will swap these around. It is incorrect to do that, and will cause problems later on when we write the formula, or when we write the electron configuration for some ions. Let's have a look at manganese. So manganese, Mn, has 25 electrons, minus 18 electrons that make up the argon core, meaning that we have 7 electrons to put into the 3D and 4s subshells. 2 are there, 3, 4, 5, 6, 7. Notice all of these are unpaired. I put into the 3D orbitals unpaired before we start to put them before we start to pair them up. Nickel, and I've taken the template away here because actually I should go back and fill in this one, 3D 5 4s2. If I was going to do this for nickel, I would find out that nickel has 28 electrons, minus 18 electrons in the argon core, means there are 10 electrons to put into here. So 2 electrons would go into the 4s subshell and 8 would go into here. Just to confirm how these would go in, I'm looking now at the 3D subshell here. I would put them in unpaired first of all, so 5, 6, 7, 8. So I'd have 2 unpaired electrons. Okay, we know hopefully from work you did in year 12 that there are 2 exceptions. And again, the way that we explain this helps to explain it, but technically isn't correct. For this part, I'm going to go with the helpful explanation, which is partially true, but isn't strictly speaking the correct way. So chromium. If we do our electron count, we find out the chromium has got 24 electrons, minus 18 electrons in the argon core, means there are 6 electrons to go in, which means we've got 2 options. We've always got to put some electrons in the 4s. So I put 2 electrons here, so that's 2, 3, 4, 5, 6. Or my other option is to put 1 electron in the 4s, because I always have to have at least 1 electron in the 4s, and then I go 1, 2, 3, 4, 5, and obviously that makes up to 6 there, so 1, 2, 3, 4, 5, 6. And we find that actually this is the preferred option and this is not. The explanation we give is that there's 2 ways to think about this. We could say that a half-filled 3D subshell has enhanced stability, or you could say it is of a lower energy. Or you could also say that this arrangement allows all electrons to be unpaired, which could pose some extra stability. I would doubt that you'd be asked to explain why this is, because the explanations that we give at A level aren't strictly speaking correct. When we hopefully get back to school, if you want, I'll go through the full explanation, but it will take a little bit of time, longer than a 10-minute video. If we look at copper, we find out that copper has got 29 electrons, so do our electron count here, minus 18 electrons in the argon core, means there are 11 electrons to go in. We've got 2 options here. We could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so 3D 9, 4s2. Or our other option is to put 1 electron in the 4s and then fill up the 3D. So this arrangement would be AR 3D10 4s1. Again, we find that this is the preferred arrangement compared to this. And again, we can talk about it that a full 3D subshell has some sort of enhanced stability or lower energy. Partly the truth, but partly not. So those are our 2 exceptions. Let's have a look at the ions. Now this is where it's been really important for us to correctly write the electron configurations as AR 3D4s, because the most common mistake people make at this point is when they're writing the formula for ions, they recognise we've got to remove electrons, but they remove them from the 3D first. If you have done the if you've done the electron diagrams the wrong way around. So let me work out how we go through this process. If we're working out the formation of an ion, the first thing we've got to do is work out what the electron configuration of the atom that it comes from is. Vanadium has 23 electrons, its atomic number is 23, minus 18 electrons in the argon core gives us 5 electrons. So vanadium itself would be Ar 4s2 3d3. So Ar 3d3 4s2. It's a 2+ ion. So we're going to lose 2 electrons. And those 2 electrons come from the 4s, not from the 3d. So vanadium 2+ has the electron configuration Ar in square brackets 3d3 4s0. Now we could write 4s0 or we could just leave it out. Either is acceptable. I prefer to write 4s0 just so that we're absolutely secure what we're talking about. So the correct answer for vanadium 2+ is Ar 3d3 and 4s0. Let's have a look at Fe3+. So do the same thing again. Fe has 26 electrons minus 18 electrons means that there are 8 electrons to go into ion, which means its full electron configuration as an atom is Ar3d6 4s2. The 3+ means that we've lost 4 electrons, so Fe3+ is 3d5 4s0. Chromium, same thing again, 24 electrons minus 18 electrons in the argon core, has 6 electrons to go in. Chromium itself is our special case, so it's 3d5 4s1. But again, we lose the electrons from the 4s first, so chromium 3+ has an electron configuration of Ar 3d3 4s0. And my final example, manganese 7, so Mn7+. Manganese is 25 electrons. 5 electrons minus 18 electrons means there are 17 electrons to go into it. The electron configuration of a manganese atom is therefore going to be 3d5 4s2. Mn7+. 7+ means it's lost 7 electrons, therefore it must have lost all of the electrons from here. So it's Ar 3d0 4s0. Thank you very much.